All right, well, welcome back to everyone who's already joined us this morning. And for those just joining us, welcome to the 2021 Fall Viscosity Summit. We just want to refresh a few reminders before we introduce our next presenter. We are going to have our next presentation from Virginia Tech, followed by a 1-hour lunch break from 12 to 1 p.m. Pacific time. At 1 p.m., we will resume with a presentation from the Blink Group and Via Innovations. They will be presenting together, and then we'll conclude the day with a presentation from Rheosense. If you'd like to connect with us, we encourage you to follow us on LinkedIn, Twitter, or Facebook.com. You can ask questions and connect with our team as well if you have any questions following the summit. If you do have questions as our presenters are doing their presentations or speaking, please ask them in the chat or the questions panel. And our speakers have allotted time for Q&A at the end of their presentations. So there will be time to get to everyone's questions. We also want to remind everyone we will send out a recording of today's summit to all of our attendees and registrants after the conclusion of the summit. Now, it is my pleasure to introduce our next speaker, Bradley Sutliff. He is a PhD candidate at Virginia Tech. Today, he will be providing insight into unique methods of using capillary rheometers as well as analytical techniques to characterize samples after they have been processed. In his presentation, Capillary Flow and Cellulose Nanomaterials, How Processing Conditions Can Impact Your Samples. Without further ado, it is my pleasure to turn it over to Bradley Sutliff.
Hello, and thank you for that introduction, Eden. Can you see my screen all right?
Yes, I can.
Okay, great. So as Eden said, I'm a PhD candidate at Virginia Tech, graduating in May. If anyone's looking to hire, just gonna put that out there. But before I move on, I need to thank the team that has gotten me this far, the Polymer Composites and Materials Laboratory run by Dr. Michael J. Bortner, and a special thanks to my undergrads that have gotten me much of the data that I'll be reporting here, and that's Sam and Nish, and also to the Macromolecules Innovation Institute at Virginia Tech, the Society of Plastics Engineer that has provided a lot of funding throughout this journey, and of course Rheosense for making my life a lot easier with the VROC, and for, of course, giving me this opportunity to present. Without any further ado, let's get into the meat. So I'm talking about basically automotive composites, or the materials that you can use in them. Many people know carbon fibers or glass fibers as composite materials. Carbon fiber you'll hear in racing bikes and racing cars and such, because they're really great at keeping your structural integrity, keeping your materials strong while also reducing a lot of weight that you would have from metals and other really dense materials. They also allow you to have lower fuel consumption and thus reduced emissions while you're driving, or make it just a little bit easier when you're climbing the hills of France in the Tour de France. But there are other materials that you can also use. Fibers are really easy, really commonly used, with carbon fibers, again, being the cream of the crop, premium, because they're so strong and not too terribly hard to make, but they're still expensive, and they're not the most environmentally friendly. Glass fibers are a lot cheaper than carbon fibers, so they're kind of the more common use material because they still provide a lot of that strength. However, they're a lot heavier than carbon fibers are, and they're only a little bit cheaper with fairly significant environmental issues and some safety issues that come up with that. So then the third one, which is what I'll be focusing mostly on today, is natural fibers such as hemp or jute fibers, or in my case, cellulose nanofibers, which can come from a wide array of sources. These are sourced from various plants. They can come from trees, they can come from algae, bacteria. You can get them from coffee beans. So they're something that is really environmentally friendly because they're built by the environment. That also makes them fairly safe. They're nano-sized particles, so there's some consideration there, but they've been generally shown to be safe. And they're really pretty decently strong for what they are, but they are weaker than glass fiber or carbon fiber for most applications, but they're also lighter weight than either of the other two. So you've got sort of some trade-offs that you have to consider anytime you're using these. But glass fiber and carbon fiber are pretty well studied. Cellulose, not as readily studied. So to get a little more information on cellulose nanomaterials, this is the structure of cellulose in the top right corner. It's just a bunch of these carbohydrate rings all linked together. And in plant cell walls and such, you have all of these polymer chains that sort of stack on top of each other to build these layers. And in some sections of those layers, the cellulose compacts really closely and becomes an ordered crystalline-like region. And then in other regions, it's disordered and a little amorphous. You end up having many micron-long fibers that wrap around each other to make bigger fibers. But if you isolate these fibers, you have cellulose nanofibers. If you instead take your cellulose material, whether it be a log or a paper filter, and put that paper filter in something like sulfuric acid, you can effectively eat away all of the disordered regions, the amorphous sections, and the tightly packed sections that make up the dense crystalline regions will remain because the acid has a hard time getting in between the tightly packed layers. And you get these fairly regularly shaped cellulose nanocrystals that are renewable. All of these materials are readily available because they're everywhere. Both cellulose nanofibers and crystals will be hydrophilic. And cellulose nanocrystals especially will have a bunch of functional groups on the surface that you can readily convert to make your material, your cellulose, hydrophobic, or have other functional groups. Cellulose nanofibers, you can do this with as well. They just don't have as many surface sites, but that makes them incredibly versatile. And especially if you pull on them or try and compact them along perpendicular to the stacks, they can be incredibly strong. To take a little closer look at cellulose nanocrystals, which is more the focus of my talk today, we can look at all of these stacked layers that build up. If you use an acid like sulfuric acid to hydrolyze them away, all the amorphous sections, you'll end up with these charged sulfate half esters, as they're called, on the surface. This allows the cellulose nanocrystals to repel each other, so they're fairly stable in an aqueous suspension. There's very little aggregation or sedimentation. And in the materials we're using, which are derived from wood pulp, so hardwood, trees, etc., they're about 50 to 500 nanometers long and can be anywhere from 3 to 30 nanometers tall or wide. And they're shaped like a cylinder or a spindle, really, because each of those layers just twists a little bit, kind of like a DNA helix. But once you have these crystals isolated from your acid bath, you usually want to wash out that acid so you can actually use them, and then you have an aqueous suspension of CNCs. You can then dry these CNCs and have a nice powder that you can then put into various polymer mixes and try and use that way. Long-term storage is pretty easily that way. However, once you remove the water, you generally neutralize those charges with counter ions such as sodium, and you tend to have problems with aggregation that you can't ever redistribute the CNCs very effectively. There's a lot of current research on trying to redistribute them, but a lot of it doesn't work very well. So another method is to use solvent exchange, where you can swap out the water for something like polyethylene glycol, and you can then evaporate off your water, and then you suddenly have your CNCs in polyethylene glycol. There are obviously other choices than PEG. Usually you'll want to do something that's fairly compatible with your CNCs, with hydroxyl groups, since it's hydrophilic, but you can also, again, do a little bit of chemistry to make them hydrophobic to put it in something like polypropylene or something. That just takes a little more chemistry, and that's not my strong suit. So what I use is never dried CNCs, where I just order a batch of CNCs from either a collaborator or University of Maine or a similar supplier, and they just send it to me where they've done all the rinsing, they've concentrated it down to 12 weight% in my case, and then from there I can dilute it with more distilled water, etc., and manipulate the concentration that way. I keep them in this aqueous suspension and test that on instruments such as the VROC, which I'll get a little more into in a bit, because I want to see what the high shear rates and what some temperature changes will do to just pure cellulose nanocrystals, because I want to keep my system as simple as possible. So I just want to look at the CNCs. So to start, we need to know what we're looking at. This is a lovely table that I've shamelessly grabbed from TA Instruments that talks about a lot of the different processes that we're looking at with various forms of rheology. A lot of people are familiar with torsional rheometry, where you have two plates or a plate and a cone or a cup and bob that are all just rotating on a mandrel, and usually that tops out at around 100 to 1,000 reciprocal seconds. That's sort of the max you can go. So there is a fair amount of data on cellulose nanocrystals at those rates and below. But what you'll notice is we're missing a large population of our processing performances, such as injection molding, blow molding, extrusion, and inkjet printing are all at rates higher than 100 reciprocal seconds. So if you want to know what those processes are going to do to our cellulose nanocrystals, we really need a way to look at those rates. And of course, many of these have similarities in that you're taking bulk material and forcing it through a fine constriction, such as a capillary. So we want to try and model that as closely as possible, because it's not going to be the same as taking a bulk sample and just rotating it from top and bottom. While that's still steady shear, we want to mimic the environment as closely as possible. So we're going to look at the kinds of shear stresses, shear rates, etc., and see what we can do to these. So for starters, like I alluded to, something like an injection molder, you start with a hopper full of material, and then you're going to try and mix it with other materials or just heat it up and melt it, and then you're going to push it through a fine constriction into a mold that may have various sizes of gaps and such that your material has to squeeze through. One of the easiest ways to mimic this is to look at a capillary rheometer. Traditionally, we have used a Instron SR20. That's what we had in the lab when I arrived there, and we've since gotten some other functionality. But this is really nice for polymer melts because it's got roughly a 60 milliliter barrel that you can fill with polymer, melt it up to 300 some odd degrees Celsius, and then push your material out. What happens is you've got this barrel that you fill with material. At the bottom of the barrel is your die that you put in, where you can restrict your contraction. We tend to use a 1 millimeter die because they're easy, and that's what we have. And then you have a pressure sensor right above that. So you can use the pressure drop from the pressure sensor above the die to the plain regular atmospheric pressure outside the die and use those 2 points to calculate how much energy is lost as your material travels through the capillary. Looking at the pressure, as you speed up to your desired shear rate, you'll end up increasing your pressure until you get to steady state, and then you'll plateau off. You grab that plateau data, average it, and there's your value that you'll use to calculate viscosity. Unfortunately for us, cellulose nanocrystals are not nearly viscous enough for the pressure sensors that come with this. We also have no desire to heat up an aqueous suspension above 100 Celsius. So we turned to other materials, other instruments that I'm sure many of you are more familiar with, which is the viscometer rheometer on a chip, or VROC from Rheosense. This has fine micron size capillaries and has the advantage of having 4 pressure sensors, so you get 4 points of data, and they are all along the channel, so there's less corrections you have to do, which again makes my life easier. But we really like this because it feels a little more true to form for something like a spray gun that you might use for painting a car or something, which is something that cellulose nanocrystals could be used in. It's just viscosity multiplier or viscosity adjustments and color adjustments in a paint. And this is the same idea. You have a barrel, in this case a syringe, that you'll fill with material, flow it through your capillary, and then collect it in your waste. What we are looking at, just to start off, because no one's really done this work before, we just got some basic shear sweeps, and we changed the temperature. Some fairly obvious things to notice is as you increase the temperature, you decrease your viscosity. That's fairly standard for most materials, especially Newtonian, such as the water that we're suspended in. And then anyone who saw the last talk will recognize the power law fit that we were able to fit to this, where we've got our flow consistency index and our flow behavior index. With higher concentrations, you have a higher flow consistency index, and with lower temperatures, you get a higher flow consistency index, and with you also tend to have a larger flow behavior index. We wanted to estimate larger shear rates, so we applied time temperature superposition to our materials. In this case, we used an Arrhenius equation to find multipliers that we could multiply against each temperature data set to multiply it against the shear rate until they line up. And then we can match that with this Arrhenius equation to make sure that everything jives well. This is really nice because where our previous data maxed out at just below 800,000 reciprocal seconds, we're now getting just above 1 million. And we've extended our lower shear rates a decent amount as well. This is really nice when you've got data that you can't necessarily hit. There's just some assumptions that you have to follow, which is that you have to be rheologically simple, which we're not really, and that you can't go through any phase changes, which we probably aren't doing right now. So those are things to keep in mind when interpreting the data. But for now, what this really shows us is that we're probably not going through any phase changes because these all line up very nicely and are shifting well. But in our next stage, you'll notice there's some other differences, some problems with those assumptions. But before we get to that, there's another error that we noticed, which is if you look right about 400,000 reciprocal seconds, you can see that there's a slight increase in our power law once we get above that. The slope of our line changes to a much steeper slope. So we wanted to look at was viscous heating above this point. Viscous heating is where you basically have frictional forces from your materials as they flow through the capillary, and they're strong enough that they are actively heating your suspension to higher temperatures than you want. So you're having a decrease in viscosity because you're not actually at the temperature you want it to be. So the quick calculation for this is the Name-Griffith number, where you use the change in viscosity due to temperature, which we clearly already gathered, your hydrodynamic radius, your shear rate, and then the heat conductivity, the thermal conductivity of your water. In our case, ideally you would have your actual suspension or solution thermal conductivity, but because we're 90+% water, and this was a back of the envelope calculation, we just estimated it as 0.6 watts per meter Kelvin, which is that of water at 25 Celsius. And what we get is right at about 400,000 reciprocal seconds, we have a Name number of 1. A Name number of 1 is sort of the cutoff of where you should be concerned about viscous heating effects. So by the time we get to our highest rate of 800,000 reciprocal seconds, we're looking at a Name number about 3.9, showing we almost certainly have viscous heating effects. That can throw off a number of our other calculations, so we have to keep that in mind, and we're planning on doing further studies into this to see how big of an impact it will have on our various studies. Our next look was to see what happens when you change concentrations. As you might expect, when you increase your concentration, you have a much higher viscosity because you're adding more solid content to your material. When you decrease it, you're pretty much just testing water, so you're also going to get much more Newtonian flow because you no longer have these cellulose nanocrystals, these rigid rods that are able to bump into each other. You're basically just testing water with a little bit of dust in it. So again, as you increase your concentration, you get your increased viscosity. We love this. This is great. However, we no longer fit power law model very well. If you notice above about 10 to the 5th reciprocal seconds, you'll see a decrease in the slope, sort of a plateauing effect. And on especially the 1.5 weight percent, which is the most similar to our water, it's starting to plateau at about the viscosity of water, which is 1 millipascal second. So what we believe is at a certain point, the viscosity of the water dominates all of our other interactions because you can no longer shear thin. You've oriented all of your cellulose nanocrystals parallel to the direction of flow, so they're no longer bumping into each other, etc. They have less of a chance of feeling each other and repelling each other, so you just sort of baseline to what your carrier suspension is. We tried to do time concentration superposition on this, following the same principles as the time temperature superposition to sort of extend our range and see if, well, could we estimate higher shear rates by using a higher concentration at a lower shear rate and then shifting it. If you look below 10 to the 5th, we don't line up at all. We have quite a few issues here. This is most likely due to problems with our assumptions. As I alluded to earlier, our suspensions are not simple. We have charged nanoparticles of various concentrations in a Newtonian liquid that can orient and interact with each other. For all we know, they can hit each other and break and just change their own size while they're traveling through this capillary. So we expect this to fail. That being said, we can still make a pretty decent looking shift factor plot using the Williams-Landau-Ferry version of the time temperature superposition equation, just swapping out the temperature terms for the concentration terms labeled C and Cref in the top right corner. And we did this all for a reference of 3 weight percent CNC in water and room temperature, so 25 Celsius. Our next step was, I'm a grad student on an unfunded project, testing all this out. So let's see how far I can get my material to go. Can I reuse my sample time and time again by just collecting it as it comes out the output of the chip? So that's what I did. I took a couple of different concentrations and just ran them through the syringe a couple of times. And what happened was, with each repetition, my viscosity decreased. What I would have expected was my concentration to slowly go up as I lose moisture from evaporation, etc. But instead, this happened. Sorry. As we increase concentration, we see a much more dramatic decline in our viscosity over time. But all of them decrease in viscosity as we continue to shear them with our system. In all cases, these were sheared at our highest rate, which was 800,000 reciprocal seconds, or just about. It was actually 794,000, something like that. And I did some quick calculations. The time each cellulose nanocrystal was exposed to these shear rates was about 2.34 milliseconds per run, or 35 milliseconds for the duration of what's on this graph, which really isn't much time to be at these shear rates when you're talking about injection molding and other processes that are going to be, pumping these through machines for long periods of time. If you look at this on a percentage basis, our 12 weight percent is losing about 25 to 30% of its original viscosity as it goes over time, and even our 1.5 weight percent, which is almost indistinguishable from water, loses about 5% of its original viscosity. So what we wanted to look at is why. Why is this happening? If you take a suspension of 6 weight percent and 12 weight percent, and you flip them over, the 12 weight percent will stay at the top of your vial because it's effectively a gel. Again, that's because of all the charges and all the cellulose nanocrystals repelling each other. They form liquid crystals of cellulose nanocrystals. The 6 weight percent, they're generally dispersed far enough away from each other that they do not gel, so it will flow to around the vial just like water would. So if you flip this over, we have our 6 weight percent, did exactly what we wanted it to. It flipped, fell to the now bottom of the vial, and our 12 weight percent stayed at what is now the top of the vial. The sample that has been subjected to 15 tests starts to flow more like honey when you flip it over. So it's not quite the same as a 6 weight percent, not quite the same as the 12 weight percent. So we really wanted to know what was happening. The first thought was, we have layers of cellulose stacked against each other to form these crystals. Maybe we're just shearing off layer by layer. Another option was, maybe they're spinning around and just hitting each other and breaking each other in half. And then we end up with much shorter particles, but they would have roughly the same width. Or maybe we're having aggregates forming and just falling out of suspension, something like that. And this is pretty unlikely because we shouldn't have any change in our charges. Everything should still repel itself, but it's not out of the question. So first we wanted to look at the shear stresses to see what magnitude they are. For our 1.5 weight percent, we're seeing 744 pascals. That's really not much. 2,000 pascals for our higher weight percentages, but this is still 2 orders of magnitude lower than what you would see in extrusion melting for things like melt fracture issues. So if these cellulose nanocrystals are breaking up in these processes, there's a good chance they're not going to survive our industrial processes. So let's take a look. If it's just aggregation, maybe that won't happen. If it's in a different material, if it's fracturing, who knows? So we turn to atomic force microscopy, which for anyone unfamiliar, it's basically taking a cantilever tip and dragging it across the surface. And every time you hit something, like a raise on the surface or a cellulose nanocrystal, it pops your cantilever up, and then you keep going, and going row by row, you can build an entire grid of height profiles. So if you look quickly, there's not much of a visible difference between 0 repetitions and 15 repetitions. But if you take one single cellulose nanocrystal from each of them and you take the height profile along the length of it, you'll have the length of your cellulose nanocrystal from where it drops off on either end, and you can average the sort of plateau region for your average height. Do this a couple hundred times for each sample, and you can build histograms. In this case, we have our 0 cycle on top and our 15 cycle on the bottom. And we start out with a pretty decent population of 300 to 350 nanometer nanocrystals, but after just 15 repeats, 35 milliseconds, we start to lose all of our 350 nanometers, start to see a decrease in our 300 and our 250 nanometer samples, and we start to see a rise lower down around the 100 to 150 nanometer. So it's quite likely we are snapping these guys in half. And if we look on just a cumulative frequency plot, you can see that there are actually no greater than, say, 325 nanometer samples in our 15 cycle samples. So what this means is we have to look at cellulose nanocrystals and their possibility to be used in industrial processes. They're great because they're lightweight, they're abundant, they're cheap. You can modify them with some decent chemistry, and they also shear thin, which can make processing them potentially a little easier or a little more difficult depending on what you're working with. However, they clearly see potential degradation from shear stress, and because they're wood, they're also not going to like really high temperatures either. And then they're not nearly as cheap and easy if you want them to be compatible with hydrophobic polymers, because then you have to spend all of the time and money changing their surface characterization. So this is just really important to keep in mind, and we'll be doing a lot more work in this area, especially on cellulose nanofibrils. Thank you for your time. I'm happy to take any questions now. And again, I'm graduating in the spring, would love a job when I'm done. Feel free to reach out to me if you've got any need for a rheologist.
Thank you so much, Brad. So we do have a few questions that have come in, and if anyone has additional questions, please feel free to drop them into our chat or questions pane, and I'll go ahead and get started with the ones we have, and as they come in, I'll read more. So Brad, someone has said, I believe cellulose is very hydrophobic. However, in your system, is lignin still present and may be involved, which can produce sulfonate and sulfates for the compounding and molding?
So we should not have any lignin. All of these are pretty purified, but with our cellulose nanocrystals, because we've hydrolyzed them with sulfuric acid, they do have a bunch of charged surface groups, which will make them both very repulsive to each other and very hydrophilic. But from my experience, even cellulose nanofibers, which don't have many surface functional groups on them, other than the hydroxyl groups that are common with most cellulose materials, those hydroxyl groups make them very hydrophilic. So I'm a little confused by the hydrophobic character of cellulose, because that's not what I've observed or read.
If they send a follow-up, I will be sure to pass it your way. Someone else has asked, each time the study was done, was the VROC cleaned? Like in between capturing samples, and regardless, do you think that contributed to the decrease in viscosity over time?
So we've looked into that a little bit. The major concern with doing a clean between each and every run is that there's dead volume that never really gets cleaned out of the cell. So if you use water to clean it out, you will be slowly diluting your material with water, or at least there's the potential for that. In general, I would expect, residual dirt and such to increase our viscosity because suddenly we've got pollutants or an increase in what was dried out material in the cell now entering our suspension. But many of these were done. We do 5 of them in a day and then do a thorough clean and then come back the next day, do another 5. And there's no noticeable difference between, the end of day 5 and the start of day 6, or in between day 6. With my other capillary, that was a problem where when we cleaned it out and for whatever reason, there was always a thin layer of cellulose nanocrystals on the inside, and we basically had to do a cleaning run with fresh material to abrade away the dried material before we could start characterizing.
Wonderful. Someone else has asked, do you think the change in slope of viscosity versus rate could be due to both shear heating and the shear degradation show by time at high rates data?
So that's possible. In terms of the decrease from repeat runs, at any given time, you're effectively testing new sample because you're unloading a 10 milliliter syringe, and you've only got 2 point whatever milliseconds in there at a time. So all of those temperature runs were from, each run was from one syringe that was run through. So those samples were never repeated, so they wouldn't have seen repeat degradation problems. And they were also at one of the lower concentrations. So I think they were all 3 weight percent concentrations for the temperature. And at 3 weight percent, you don't see a significant decrease from one run to another run. It's just when you look from at run 1 and run 15, which we would not be doing in that case.
No, go ahead.
Sorry. But I will say in actual processing, that would definitely be a concern because you would be both heating up your sample, and depending on how long your flow channels and such are, you could easily be breaking up your material that entire time while viscous heating, and just from start to finish, you could have a drastically different viscosity, which you can calculate if you know what, you can account for if you know what you're doing and what to expect. But without that information, I can foresee a lot of problems.
Now, the next is a comment, but if you have any insights or feedback, we'd love to hear it. Someone said, CNC have always needed a lot of dispersion energy to disperse. Maybe studying bentonite clay dispersions would be a useful house of cards versus dispersion in flocks.
So that's a good point. The nice thing about working with cellulose nanocrystals that are never dried is they do stay quite well dispersed. Cellulose nanofibrils, on the other hand, those are just pure flux. And some of the data that I was hoping to share today, but didn't quite get the paper submitted in time, is on dealing with those flux and how you can process to get around it. Bentonite clay is something that is interesting to work with. It's just not something that we have super readily available to us, but it would be interesting to look at.
So the next is a multi-step question a little bit, and I'll read the whole thing, and if you need me to go back, just let me know. So given that is a linear molecule, you could test at very low shear rates to try to attain the terminal region and check if you may have variations in molecular weight after testing the sample the 15 times you mentioned. Did you carry out oscillatory experiments in order to see what was happening with the molecular structure, or try to obtain also the linear elastic compliance?
So this is something that we're currently working on. As for using it in a rotational or torsional rheometer, a lot of the 3% suspensions are too low viscosity for the geometries that we have easy access to on campus, which is sort of why we turn to the VROC, is because it can get those shear rate. It can get good shear data from both small amounts of material and very low viscosity materials, whereas what we currently have for a setup for our torsional rheometer, it's much trickier to do that for. It's also difficult because cellulose, especially once it's in nanocrystalline form, is not quite so easy to run something like SEC or GPC on, because all of this linear chains are stacked up and very closely held together, and it doesn't dissolve, but it stays suspended well. And so maybe this is where the confusion from the earlier question with hydrophilic versus hydrophobic comes in. But the actual crystals don't dissolve in water. They just stay suspended. And there's not many solvents that will break up those crystals and dissolve them into something like a free chain cellulose. You can use some ionic liquids, but what I've seen of GPC and SEC operators is they're a little reluctant to let us use those ionic solvents in their instruments. So we're currently working on trying to do that, but I would love to have a discussion with anyone who has some great ideas on dissolving cellulose nanocrystals and looking at that. Because right now the best we've got is using atomic force microscopy to look at the actual holistic crystals.
Wonderful. And before we break for lunch, I just want to make sure, does anyone else have questions, comments, any further discussion they'd like? We do still have a few minutes left during Brad's presentation, so please do drop them in the questions or chat, and we can wait just a minute to see if anything else comes in. And if there are not any further questions that come in, I just want to say thank you again, Brad, for your time today. Thank you for participating in our summit and for this wonderful presentation. Please feel free to connect with Brad. His information is still on the screen right now. And again, we will be sending out the recordings once the summit concludes. And so you'll have his contact information via recording as well.
Thank you again, Eden.